All right, let's get started. Today we'll hear from Shibhansh Dohare. He's a master's student here at RLAI, and he's going to tell us about the interplay of search and gradient descent in semi-stationary learning problems.
Right. Hi everyone, so I'm Shibhansh. I'll be talking about the interplay of search and gradient descent in semi-station learning problems. So this work was done with Rich and Rupam. So let's start by talking about what semi-station learning problems are. So these are an instance of online supervised learning. So online supervised learning means that that samples are provided one by one. However, we add a couple of new properties which make the setting a lot more interesting. First, instead of having IID data, we focus on the case when the inputs are temporally coherent, which means that the input at time step t is dependent on previous inputs. And we formalize this by focusing on the case when the inputs follow a Markov chain. And second property, which is potentially more interesting, is we make the target function, which is the function that we want to approximate, and we make that function to be more complex than the available approximator. The performance measure for this setting is the online loss, which is the loss on the next example. So we do not care about average loss over the entire input space. We just care about the loss on the next sample. Okay, so let's look at an instance of this problem setting. So there's a two-dimensional input where the input travels in a circle. So the circle is centered at the origin, and input moves around slowly at a rate of like 1 degree per time step. And the target function is x squared, but the available approximator is just linear. So we cannot exactly represent our target function with this approximator for the whole space. And for this case, the loss function is a squared loss. Let's try to think about what are the possible solution strategies. First, what we can do is to do the thing which is the common thing in supervised learning, which is to find a stationary solution. And that is usually done by using stochastic gradient descent and converging to a local or global optimum. For this problem, though, we can analytically find the best stationary solution, which happens when the weights are 0. And for this case, the average is 0.5. However, we can do better than this. We can do better than a stationary solution. Since the inputs are not inputs are actually temporally similar, what we can do is we can focus on the current part of the input space where we are and try to find an approximation which is good for the current part, but is not good overall. So for this case, we can use a simple stochastic gradient descent algorithm. And if we use it with step size of 0 and weights initialized at 0, we find that it can actually do better than the stationary solution. So in this plot, this orange line is the stationary solution. This is the average performance of the stationary solution. And the blue line is the performance of the tracking algorithm, which is stochastic gradient descent. Okay. Are there any questions up to this point?
Yeah, just a quick clarification. So what exactly do you mean by semi-stationary?
Right. So I'm saying semi-stationary because the target is actually stationary. The actual target function never changes with time, but the input distribution does change with time. So it is somewhat, so it is not actually non-stationary, but it should not be treated as stationary. So we are using the term semi-stationary. I hope that makes sense. Okay.
Also, why is the online loss lower in the beginning than it rises to the top? Shouldn't it be the other way around?
I don't know why that's happening, but I don't also understand why it'll go down with time. Because I'm not decreasing the step size, and there is one level, right? So the step size is like a 0.1, so it should learn around the average of last 10 points,
right?
Something like that. Okay, let's look at a bigger problem, which is potentially more interesting. So I'm calling this the bit flipping problem. There are m+1 bits. So the last bit is always 1, so it's spice unit. Rest of the bits, they flip with the probability, which is somewhere between 0 and 0.5. The interesting thing to note is that when this probability is 0.5, the the value of the bit is distributed IID, and as it gets closer to 0, the inputs become more and more correlated with each other. And the target function for this case is a neural network with a single hidden layer. This neural network has LTUs as the hidden units. So LTUs have an output of 1 or 0, and this output is, of course, not differentiable, and it is also not continuous. And the output of the network is a single number, which makes this a regression problem. And again, we care about this. We care about the squared loss. Okay. So let's look at an instance of this problem. There are 21 inputs, of which 15 bits flip slowly with probability of 10 raised to the power minus 5, and 5 bits flip fast with probability of 0.5. And the target network is big and has 80 LTUs. And the approximator is also a neural network with 1 hidden layer, but it has just 5 hidden units, and it is using 10H activations. Okay, so if we use backprop, this is what we find. So what seems to happen is that backprop does well for the first few thousand, 10,000 time steps, but it gets worse over time. And this is interesting. So let's try to think of what exactly is going on here. So every time one of the slow flipping bits flip, the input distribution changes because the fast flipping bits are essentially just IIDs. So every time we change the slow flipping bit, the best local approximation that we are trying to get to, it changes. So we are at some point, we have, let's say, converged to some point for the current distribution, and then the bit flip, and we now want to go to that next point. So the main difference between time step 0 and time step 1 million is that that initial point has shifted. So initially we started with some special distribution, and over time, after learning, we have moved to some different part of the weight space, and it seems like that is not a good starting point if we want to track. So it seems like the input distribution is important, and if we can somehow infuse that input distribution in the current while tracking, then we can probably do better. So how we do that is using generate and test. So
I have a question.
test. Oh, sorry. Yeah.
So how are you using backprop to train this? Are you using it one sample at a time? Are you keeping batches around?
No, I'm training purely online, one sample at a time.
So what's the key takeaway from that? Can you summarize it once again? Like from the previous plot, what should I
that backprop gets worse over time. And this happens for almost all activations and all learning rates, all reasonable learning rates. Like I can show at the end of the talk, plot for other learning rates too.
Sounds good. Thanks.
Okay, cool. Okay, so generate and test is a search process in the space of features. When I say features, you can think of hidden nodes. So so generate and test process has a tester which finds what are the bad features, and a generator which produces new features. So we find low utility features using the tester and replace them with the features that are provided by the generator. For this problem, we'll be using a random generator. So the new features are generated randomly from the initial distribution, and the tester is based on the magnitude of the outgoing weight. And I'm using a replacement rate, a small replacement rate, which means that I'm replacing around one feature every 20,000 time step. And when we do that, we find that it helps backprop over time. This is a plot on the log scale. So as you can see that the performance is significantly improved when we use generate and test with backprop. The final error is around half of the error that we get from backprop. Okay. Are there any questions right now? Okay.
So what does the approximator look like in this case? So what do you mean by backprop plus generate and test? Like what specifically does that mean?
Right. So that means that at every time step, I'm getting a sample and I'm doing backprop and changing the weights. And once every 20,000 time step, I'm removing one of those 510H features and reinitializing the weights to some random weights.
So when you apply backprop, do you update all the layers of the network?
Yeah.
So it's not like a loop bit that you only train the last layer and then you replace features. You're training backprop and you're replacing randomized features.
Yes.
So
Rupam, sorry, just a second. Rupam at the end of his work also did the same thing. Like he trained via backprop and also replaced a little bit.
So why should this help? So the thing that I'm having a difficulty understanding is that backprop is sort of destroying whatever it's learning because of temporal coherence, and you're also replacing things. So you should, if anything, you should make it worse because you are replacing whatever you have, and you're not preserving what is useful because backprop is sort of updating those things anyways.
Right. Okay. I'll try to explain, or at least give one reason that I think explains this phenomenon. So let's look at the nonlinearity that we are using. So what we are using here is the 10H activation. So when I use the word activation, it refers to the output after the nonlinearity, which is 10H of the W transpose X. And if you look at the derivative of 10H, this is the purple line. You can see that it is high. The derivative is high when the input is when the output of 10H is close to 1. And in this case, the input space is all possible combination of bits, which is 2 to the power 20 combinations. And if I look at the average activation of for a random feature, I've looked at the average magnitude of the activation, not the actual value, the magnitude of the activation. I find that this value is very close to 0. So initially, the derivatives are very, very high. Let's look at what happens if I train it after 5 million time steps and what features emerge with backprop. So what I find is that these features have a very high activation. And in this part of the space, the derivative is very, very low. So whenever the input distribution changes, whenever we want to get to a new local approximation, it is not we cannot do it very well because the derivatives are, the gradients are very small. So what seems to happen is that features get stuck in regions where there is a very small gradient. So it is much harder to learn new functions now. If when we continually inject randomness using this generate and test process, it helps in keep the features closer to the initial distribution, which has high gradient, and thus it is much easier to adapt. It's easier to get to new good approximation. Does that make sense to you, Zahir?
So, do you want to say something?
I'm still a little confused, but I'm still processing, so I think it will all come together as we go forward.
So the problem is, the problem that you're highlighting in this case is because you have an activation function which saturates, and then because when the distribution changes, it's hard to go back to a different solution because your gradients are small. But that means that if you did not use an activation function which saturates, then SD would do fine.
Right, but for almost all nonlinear activations, there is some region where this gradient is low. So even for ReLUs, this happens. Yeah, Chaba.
Yeah, can I add something to this? So this totally reminds me what happens in very simple scenarios like experts, prediction with expert advice. Yeah, leaky ReLU would be one example. That's true. But so in prediction with expert advice, you are on a probability simplex, and if the experts are changing up, like who is the good expert, the identity of the good expert changes over time, and your distribution ever gets too concentrated on one of the experts, then there's no update rule that would save you from, like getting stuck with that expert forever. Even if you would get the information that, oh, this expert is better, it just takes forever to remove the weight with this learning route, this gradient-based learning route, even with exponential weighting and whatnot. So what people were doing there is that you just prevent this happening. So this saturation should never ever happen. So the natural alternative for all of this, well, you could try some nonlinearities that don't have any saturation. Maybe this completely saturated points could still be going up or whatnot. But I think maybe it's better to just limit the range of the outputs or the range of the weights, right? Just put some constraints in there that the activation shouldn't go outside of the unsaturated region, because if it does go outside, then this unit is completely useless.
Well, how can we do that?
Increment on that, and then add some decay. And if you do some, I don't exactly know how to do this, but this seems like the most natural thing to do to address this problem. I mean, in similar situations, this is what people do. In this setting, it's a little bit more complicated, but I would definitely try to investigate whether something like this is possible.
Right. Right. But if what actually happens is that instead of weights becoming very high, just the output of the feature somehow becomes very high for some inputs.
So it's an activation. Yeah, you want to constrain you want to constrain the weight such that the activations on the average or whatnot don't get this bad region.
I see.
So that means coordination between the input weights. But that shouldn't be too hard to do. If you have some pattern of activations, then you can, keep the weights in a region such that this doesn't happen. It's like a little penalty here and there would do this. Just penalize large activations. You can write a gradient rule for that. Just to add to the loss. Something like that.
Okay. I guess there are some comments. So Andrew asked, is this different than using dropouts? I have not tested that, so I'm not sure about that. And Matt says regularization, but I'm not sure about regularization on what.
I have a comment here, which is that since you're talking about these two different problems, one is that you're getting close to the boundaries of the space where you don't get a signal, and then the other is right. And the naive solution to both these problems is somewhat opposed. So what Shaba was saying, staying close, for example, on the simplex, not getting close to the boundaries of the simplex, usually the naive way to accomplish that is to just pull yourself closer to where you started from, right? And the other problem, which is to achieve tracking, the way to get tracking is to have high learning rates, right? You don't want your learning rates to shrink very small as time goes on, because then you can't track anymore. And if you just naively put both of these things together, it seems like it can't work. Because if you have high learning rates and you're moving far away from where you started, but then you're also getting low signal. But of course, this is because you're doing this naively. And there are all sorts of ways of doing this that are sort of more sophisticated, that are more careful about avoiding the loss of signal, but also maintaining tracking, right? And later I can give you, I found a very exciting paper at the latest ICML that addresses this, so we can talk about it later.
Okay, awesome. Yeah.
I have another question. Can you go back to the slide in which you show the difference between generated test and SGD? Yeah. So for this specific problem, it seems like when you start from completely random features, those features are already pretty good. In fact, you're running losses, and then it increases because you go to the saturation points, which are...
No, this is actually the loss average over the last 10,000 points. So initial loss is around 1 order of magnitude higher than this loss. So it starts around 1. So this is, the initial point is actually average of first 10,000 points.
Right. So what I'm saying is, even in that case, the initial features are pretty good. Is that true? The initial random features are pretty good.
No, they're not. I'll show you the graph which actually shows the performance at starting point, and that's not good.
So I don't mean the exact initial. I mean you start with initial features and you do some steps, and it becomes very good because at that point,
Yeah.
really good gradient. But then you think saturate. But that's why good because you're in this specific problem in which those features are good. But eventually you want to learn features where discovering good features might be extremely hard. So it might take a long time to discover them. And if you keep on overriding them using randomness, that just might never happen.
Right. So I'm not saying that this is a perfect solution, but I'm saying this is better than just doing standard backprop.
No, that's true. The solution that Rupam proposed in his like the first one, that has this nice property, right? In that case, you're never removing good features. You're only removing bad features and you're replacing them with something random, which can be better. So eventually you might have good features.
Right. So that is the exact process that I'm doing. So if there are good features, they will not be removed. Okay. So let me just conclude now. So the first takeaway is that if the inputs are temporally coherent, then it's better to track a local approximation than to converge to a globally optimal solution. Of course, this is true only if the target function is more complex than the approximator. The second, and I think the main takeaway, is that the initial distribution is critical for fast adaptation. And next, I find that the internal representations that we learn from backprop actually hinder adaptation. And the slow continual injection of randomness helps backprop in tracking problems. Okay. Yeah, that's it. Thanks. The questions?
Can we go back to the plot?
Yeah.
So to me, it seems like both of them are not working.
That is what you mean by working.
Yeah. So can you explain how to interpret this difference, right? So are we comparing, let's say, garbage with garbage, or this difference is actually substantial in terms of so how can I interpret this difference in loss so that I can have a sense of how much better it is, or is it just that both of them are not working?
Right. So that would be easy to do if we have, let's say, some optimal solution. Then it'd be easy to compare what's the best that we can ever do. But in this case, that's not the case. Maybe if we think of it starting point is like the best that we ever get to. Maybe if we can remain close to this will be the best possible solutions. But that, of course, doesn't seem to happen.
I have a quick question about your conclusions, if you could go back to the last slide.
Okay.
Like the first point of it says that if the input is temporally coherent, it is. So can you talk about what the complexity of the approximator classes has to do with this, and what does a globally optimal solution mean? Right? It's saying it's better to do this than to do this other thing. But what does that mean?
By complexity, I mean this is important because if we can exactly represent the target function, then we don't necessarily need to track. We can just find one stationary solution, and that will solve everything. And when I say globally optimal, I mean global for the entire input space, for the whole input space. If we try to find a solution that is good for whole input space and fix that solution, then we can maybe do better than that.
And that's because
sorry,
go ahead.
No, go ahead. Sorry, finish the discussion.
I was saying that. And that is because in your setting, because you are separating the target into two parts: the distribution of the samples and the target function. So in principle, if your class is big enough, you can find a function that works for all distributions.
Yes.
Okay.
Yeah.
Okay, so I was asking that, so we are seeing that backprop is not working. Is it because it has insufficient capacity, or is it because the data stream is temporally coherent? So let's say if I make my data IID, but fix my capacity to what we have, what does the solution look like? Is it?
Okay. I think it'll be, in this problem, it'll be slightly worse than this green line. It'll be worse than this green line. So it'll be worse than backprop when we're just tracking. And yeah, both of the factors need to be there. If you're just doing IID, then it's not clear if adding anything of generate and test will be very helpful. And if the stream is just temporally coherent, but the function is not too complex, then maybe eventually we can converge to a very good solution.
Yeah, it would be interesting to see what happens when you have IID data and batch setting and you are doing the typical supervised learning thing, but you have insufficient capacity. Does tracking with backprop and with backprop plus generate and test help there?
But if the input, if you're just using IID input, then why will tracking do any better than
it won't. But I just want to
Right.
isolate the effect of temporally correlated stream of experience and having insufficient capacity, because we know that backprop also sucks when you have a temporally correlated stream of experience. Right. So yeah, it would be interesting to see how those two effects, how those two problems relate here.
Okay. Yeah, I'll look into that, I think. Yeah, so I think Zahir pointed out, or Khurram pointed out, if we use other activations, this might not happen, but I find that this actually happens even for ReLUs. So this is for various step sizes. As we can see that if we have a small learning rate, which is represented by red colors, it is always bad. If we have a high learning rate, it's initially good, but then it gets worse over time.